Hi everyone, I guess we're going to start now with Adeline Paiement from Université de Toulon on a general overview of machine learning and deep learning stuff.
Yes, it's a quite large topic, so I'm going to be very brief and do something very condensed. There will be a break at the middle to give room to ask questions, but don't hesitate to interrupt me if you want to ask questions before or get more details on something. So I'm going to, why is it not? Okay, there's a bit of lag. I'm going to skip this really quickly because we already had a round of introductions this morning and go directly to the talk. So we're going to see a very brief overview of machine learning and deep learning. I'm going to go over very quickly over some basic principles underlining unsupervised learning, supervised learning with some examples, mostly using images because they're really nice examples to illustrate what I'm going to talk about, although this is not restricted to images. And I'm going to try and give you some hints on how to use these methods in practice, some good practices. And hopefully this talk will give you some clear ideas of what is possible with machine learning and how this can be deployed. I'm going to also introduce neural networks, which are just a family of methods from the machine learning area. And here again, this is going to be a bit of theory and then a bit of practice on how to use these methods. And so we'll do a short break here in the middle. So I'm sure all of you are interested in, well, if you are interested in machine learning or deep learning, this is because you are facing a deluge of data. And this is happening in all sorts of areas. And so machine learning and deep learning have been developed to address these issues in many different fields. So you have methods that you can use which come either from, which have been developed either specifically for your data or most of the time for different data and different problems to solve. But they all have things in common, the first of which is the sheer amount of data and the fact that we want to extract useful information from these large data sets. So this is exactly what these methods are trying to address. And you can see here a very quick illustration of the growing number of data that started quite early in even in the 70s. People have been starting to think about using machine learning or AI in more general to address information extraction from data sets that were growing larger. And when do you want to use machine learning, which is a kind of statistical modeling? You want to use it when you don't have enough knowledge to build a mathematical model of the thing you're studying. If you don't have the knowledge, or if the task to be modeled is really complex and you have very complex relationships within your data. And in this case, this data-oriented statistical modeling can help build a model which is not analytical, but which will fit your data and the process underlying their data. Of course, this only works if you have enough data available. You need to have something that's representative of the process you're trying to model. Artificial intelligence started developing quite long ago. So in the early 60s, machine learning, statistical machine learning, is only a part of AI. AI is a much bigger field, and if you zoom in, deep learning is a part of machine learning. So we are here looking at a specific family of methods, but there's a bigger picture, a bigger research area around it. But as I said earlier, the main objective of these methods is to extract the meaningful information from that is contained in the data, and do that as automatically as possible. A quick word about data challenges. This is something very fundamental that is faced by all people who are deploying machine learning methods. And I'm not going to talk about cleaning the data and things like this, but you have to, what is called curate your data sets before you can do anything with it using machine learning. And so you have a lot of usually a lot of time spent in preparing your data, in thinking about what methods are the most suitable for your data. And data can be of a lot, can come from a lot of different sources with very different nature, from images to sound, text, graph sequences, spectra, etc. The take-home message in this slide is there is no universal solution. You will need to pick the method that really suits your data and the task you're trying to solve. So it takes sometimes a bit of time to first prepare your data, deal with all the defects, because the computer will not be able to automatically deal with them without your help. And then pick the method that the most suited for your purpose. And you'll see in a few seconds that there's a lot of different types of tasks that can be addressed with machine learning. And sometimes a problem can be solved through different routes with different approaches, different methods, but you're not always the same one. So there's a bit of expertise here that is needed to pick the right type of methods and the right type of problems that will solve your that will solve the task you're aiming for. So in general, the data processing pipeline looks like this. So after collecting your data, you have a step of preparation, I just said, to deal with all the issues with the data, but not only. That's what I call here the cleaning, but you also have some data preparation that aims at preparing the information extraction, presenting the data in a format that is more readable, and where the information is easier to find and extract. We're going to see a few examples in a minute, and I think you'll see more this afternoon. And then after that comes the learning part, although some of these can use learning as well. Where here we're going to address really the learning task we're interested in, be it classification, regression, etc. So there are in general, four main types of problems that you can address with learning. The classification is a very popular one that everybody knows about nowadays, because all the deep learning fancy networks that are very popular, they usually do classification. So people are well aware of that task. But you can also do clustering, so grouping similar things together. Outlier detection, which is kind of related, although it's the opposite. You're trying to identify the elements in your data which don't fit with the rest. and association pattern mining, which is less well known, but also quite important and used a lot in some fields. So this is trying to find patterns in your data, which is also related actually to the other three. In many cases, there are multiple ways to tackle the same problem, and you may address it as the outlier detection or as the clustering or association pattern mining, for example. So how you phrase your problem using these four possible main types of methods will determine which method you're going to pick and how you're going to, from which angle you're going to tackle your problem. Let me give you a few examples to illustrate these four main tasks. I'm going to focus actually on the two most popular ones, the clustering first. So as I said, clustering is grouping things together. And these things, I use a very generic word because it can be anything. In this example, the thing is the pixel value. So we're trying here, people have been trying to group pixel values together to identify areas in the image which have similar properties, which show the similar thing. So you have different versions here, grouping, depending on which criteria has been used. You could also have a grouping of images of spectra, trying to group, for example, here all images of a similar objects or similar scenes together and building here a graph of images. This is just illustration with images, but you can imagine grouping of any types of data. Now classification is identifying which group your observation belongs to. And here again, the group can be of anything. In these two examples, here the group is the type of bird. Here the group is, so you're classifying an observation, a full observation of bird. Here you're classifying a pixel. So you're trying to find in which group your pixel, does it belong to the dog or to the background? And this is called segmentation. So again, you can classify a lot of different things depending on how which angle you tackle your problem from. We've been, so to tackle this full task, you may have different types of learning available. Learning comes from unsupervised, so where you only have data and nothing else, prior knowledge on this data, to fully supervised learning, where you have the data and you have a full description of your data, which you can use to learn how to describe a new piece of data that comes in and that you don't already know. And then you have all the levels in between. You could have a semi-supervised learning. So you're in between the unsupervised and supervised in the sense that you have annotated a part of your data set, but not everything. And you can learn still from, you still want to learn from everything. So you have to deal with missing annotations in some of your data. And then weakly supervised learning, that's an interesting one. You have annotated that you have a data that's annotated, but the information that the annotation is only partial. So for example, you are looking at solving a very complex task, but you have annotated your data in a more simple manner. For example, you wanted to do segmentation like this, but instead of annotating every pixels, you just draw a bounding box. So you have less information than annotating every pixel. You just know that the dog is in this area, but you don't know which pixels exactly belong to the dog and which belong to the background. So that's a different task, which is simpler, but contains a part of the information you're interested in, but not everything. So that's called weakly supervised learning, and that is becoming increasingly interesting for the AI research community, because as you can imagine, annotating complex tasks extensively on a large data set is very costly, very time consuming. And so annotating the data more simply is quicker, or even annotating only part of the data. All of that is more realistic to deploy in real scenarios. And so there's more and more research being done in these two fields. I'm not going to say much more about that today because we don't have time to cover this extensively, but be aware that this exists, and there's a lot of research being done right now on these topics. And this is worth keeping an eye on, because that is what allows you to solve real complex problems in real life when you don't have the mean to annotate fully a large data set, especially when it comes to deep learning, where you need a lot of data to train your method. So just to illustrate unsupervised learning, I'm not going to describe unsupervised learning a lot this morning either, because there will be more about it in the next lecture this afternoon. But there are different tasks that you can solve using unsupervised learning. The idea of unsupervised learning is that you don't know the data, you don't have prior knowledge about it, and so you're trying to discover what's hidden in it. So you can use that to do clustering, so to group the data. You can use unsupervised learning to change your data into a representation that's more easy to work with, that's more easy to interpret and to understand. And so that will be more easy for the machine learning for our supervised learning step that comes afterwards, for example. That can also be used to reduce the dimensionality of your data. Here we went from 3D to 2D, for example, but that can be much more drastic. You can use that to also find interesting trends in the data. For example, here you can see that your data is distributed mostly along these two axes, and so you can use that to represent your data in a more simpler way, which uses this description. And you can approximate density functions, etc. There's a lot of other interesting uses, but these are some of the most popular ones. So this is all about exploring the data, trying to get some more better understanding of it. I'm going to skip this since you'll see that a bit more in the afternoon. So now from now on, we're going to focus on supervised learning. Supervised learning has developed a lot recently, well, in the past 10, 20 years, with the advent of very large annotated data sets. So it's a step that may come after the unsupervised learning. And it requires both the data and its annotation. The annotation being specifically the task that you want to solve, because we're looking at fully supervised learning. And as I said, we're not going to cover weekly or semi-supervised learning. So here we are looking at a task of segmenting. So we have annotated every pixel into a category, so a person, a motorbike, and background. And you have to do that for all your training images in order to train a fully supervised method on segmenting your images. We are making one very important assumption in the supervised learning scheme, which is that your data is really well representative of the things that you want to model. So if you only have motorbikes in your data set, your network is not going to learn to classify, I don't know, boats or dogs. You have to make sure that your dataset contains all the things that your method is likely to see in the real life later. so that it can learn about it. And so, as I said earlier, this supervised learning has become very popular because there's been very large data sets that has been annotated and released, and they can be used as benchmarks to train and compare the performance of learning methods. Some popular data sets are given here for images. There's many more, and not just for images. But the interesting things to consider is that these data sets have been prepared for various different tasks, learning tasks. Some are for segmentation, some are for classification, and so they come with different types of label. Here, pixel-wise annotation, here a category for each image, or the classification, etc. And so to start with an example to illustrate, so when we do a classification, let's say of images, we need to associate one label to one image. What is a label? In classification task, label is a scalar. Simply a scalar, it could be 1 or -1 or 1 or 0, where 1 means, in this case, the image shows a face, and -1 means the image doesn't. So it is as simple as that. But then, together with this label comes an image. And in general, the learning is not performed directly on the images. It is performed on some features, some descriptors of the image, which is the task I referred to earlier on of transforming the data into something that's more interpretable, where the information is easier to extract from. So this is usually the first stage of information extraction. And it can be done with demonstrative reduction. So it also helps reducing the dimensionality, so learning is easier. And I give here an illustration of one very visual descriptor, which is a bag of visual words, where you have little vignettes, very little patches of basic shapes, and you have these kinds of histograms here of how many times these basic shapes have been found in the image. With this very simple way you describe the image content. This is not the most popular descriptor by far, but it is very visual, very easy to illustrate the concept. But you can imagine plenty of other ways to describe an image. One very popular way is to look at all the gradients in the image to find edges, very strong edges, strong gradients, and then build a histogram of the orientation of the gradients locally in lots of patches in the image. And that gives you an idea of the shapes that's contained in the image. Or if you're interested in textures, you can look at more at the statistics of the image, etc. There's lots of possible ways of describing an image based on what information you are interested in. And so engineering a good image descriptor also requires a lot of expertise, can be very tricky, and you'll see later that's why, specifically why deep learning became so popular, because it helps automating this step. So once you have defined your labels and your image with a nicer way to describe it, comes the actual classification task. And the classification is just finding a function which does the mapping from the descriptor, here X, to the label Y. So learning a classifier is an optimization procedure where you're trying to identify a mapping function from descriptor to label. And with usually some parameters of the method that needs to be optimized in order to adjust the mapping. Here, just a quick example with the SVM where your mapping is provided by this very simple function, which is trying to find a boundary between two classes and by maximizing the distance between this boundary and the data points on either side. So that's one very simple way of classifying. So finding this very simple function. In general, this function, so it's here that your function, your mapping function, is found by minimizing the error it has in associating the data point to its label. And so you compute this error here, which is called the total risk, as all the possible errors that this function would make on all the possible observations and labels. This is a very exhaustive function, which obviously you cannot compute in practice because you cannot consider all the possible data. Therefore, this is usually approximated by what we call the empirical risk, and that is a very key element in machine learning. This is at the basis of all learning, supervised learning methods. So you're computing all the sum of all the errors of your classifier on your training data. So all the data you have available to train your method. So you're applying your mapping to your training data and you compare the output with the real label. And this function here, which is called the loss function, is a function designed to compare your label and the mapping that is provided by your classifier. And you'll see in a moment that there's lots of ways to compare that, obviously, depending on what there is the nature of your label and the nature of your task. And so this function is what is minimized in order to train your classifier. Usually this is done using gradient descent or improved version of gradient descent. So now in practice, since we only have a finite number of samples in our data set, we have to ensure that this empirical risk that we are computing is really representative of the real risk, the total risk here. This can be a very challenging thing, but it can be shown that if you have a sufficiently large data set, the empirical risk tends towards the real risk. So that is a guarantee that if your data set is sufficiently large, this way of tackling the optimization problem actually works. And your model's parameters tend towards the optimal model's parameter. Now the big question is how large is enough? And that's a very recurrent question in machine learning. And again, there's no universal answer. This always depends on the task, the modeling task, and the complexity of the task, the complexity of the data set, and the complexity of the model. Now, there are a few tricks to ensure you are in the best position possible when you do the learning. The first one is to divide your data set into two subsets, one that is used for training, so optimizing the parameters of your model, and one is kept aside for testing. And it can be shown that the empirical risk that you compute on the test set after you do the optimization, this empirical risk tends towards the total risk. And the parameters of their model when it's trained on the training set tends toward the optimal parameters. This split is important to test what is called the generalization. which means if you train your model on some samples, of course, if you present the same samples, you can expect that it will give you the right result because you optimized it. You optimize the parameter of your model so that it gives you the right results for these specific samples. But if you present samples that has not been seen during training, so we did not take part in the optimization, you can test that the model can still predict good labels for this data, which is not known. So the optimization has not been done on the test set. It was not part of the empirical risk calculation here. But still, you would like your mapping to work with this data and to produce the right output. And so that is called the generalization. And so if you do this division, you can ensure that your optimization produced a working model and not just a good memory of the training data. Again, to have a good generalization, you need to have a sufficiently large training data. And again, the question of how large is enough can be asked. So there are some very recommended solutions, again, to help you be in a good working scenario. You can do random sampling. So you pick test samples randomly in your data to ensure that you don't have, I don't know, all the data of one class for training and all the data of another class for testing. You want to mix things up so that you see a bit of everything during training and you test on a bit of everything. So random sampling is really important. And then another interesting thing is to train several times, several models with different random parts of your data so that you can test also on different parts of your data. And actually that can be formalized into this approach, which is really classical in machine learning. It's really recommended to use it. It's called k-fold cross-validation. So you divide your metadata into k-folds. Here we have 4 folds. You can pick numbers, of course, but the key thing is to keep 1 fold apart for testing, train on the rest, and then do again. Keep another fold for testing, train on the rest, etc. So here you do 4 training on 4 different data, and you test on 4 different data as well. And with this scheme, you test on every data once. So you test the generalization really well, and you make the most of your data. Basically, you train on everything and you test on everything. And that's the most optimal way of using your data, of using as much data as possible for training. And you get the best possible estimator of your risk because you're averaging the risk for each model you trained. And there is an even stricter way, a stricter scheme, which is to keep just 1 data sample out for testing and training on everything else. This is particularly nice when you don't have much data and you want to train on as much data as possible on each run. Of course, that gives you a lot of computation. So this is reserved for really small data sets. Okay, so in practice, your models also have what is called hyperparameters. So things that need to be chosen before starting to train. For example, in neural networks, that's number of layers, number of neurons, or SVM, constant power equalization, etc. So you have some parameters that are that need to be optimized, which are not part of the mapping functions parameters. And so you also need to optimize these parameters, and you should not do that on the same sets. So you have to actually divide your data into 3 sets, one for training, one for testing, but also one which is called validation sets for optimizing the hyperparameters as well. So that's a bit more complex scheme, but that's the good practice of how you should train a machine learning method. If you want to be sure that your results are really representative of the results you're going to get when you deploy your method in practice. I think the slides will be available online, is that correct? Yes. So I'm not going to detail that too much. You can refer to the slide later if you need it. Right, so once you train your methods on the training set, you can here what is shown is the error, so the risk, the empirical risk, and here is the time when you're training, beginning of training, and then as you train more and more, because you're optimizing the empirical risk on the training set, it should decrease. That's the point of the optimization. You're trying to minimize its very function. But now on the testing set, usually the risk decreases up to a point and then it starts increasing again. What's going on here is that on this test set, which is not seen by the method during training, the empirical risk is not optimized for that data. And so at the beginning, as the method is learning, it's learning to model the task you are interested in. And so it's learning to, let's say, if it's classification, it's learning to classify your training data, but it can still adapt to generalize to also unseen data in the testing set. And so the classification is getting better and better on all the related data. Up to a point where the method, so that's when, if you're trying to classify to separate the green crosses from the red circles, for example. So you start with a bad classifier, let's say that's a straight line. And then you start getting something more like the dashed line. So something that separates them more and more, well, better and better. And so you get a better performance and lower error on all the data. And then after some point, your model is going to specialize so much on your training data that it's going to start doing this weird here wiggly thing to try and really match your training data at best, because you are optimizing on this data. So you're trying to minimize this function as much as possible. So it's going to try and find the mapping that optimizes this, that minimizes this function. And so when the minimization here becomes too drastic, the mapping becomes really too specialized for this particular data, then that's when it starts going wrong for the rest of the data, because they are not taken into account when doing this very, very fine mapping. And so that's what is called overfitting. So that's when the model is starting to be so specialized towards this particular data samples that it doesn't generalize well to the real data anymore. And so that is something every supervised learning method will fall into if you continue the training too much. And that is why you really need to keep the testing set aside to verify what's going on, because otherwise you won't notice that the error on new data is increasing. And so you may think, oh, that's great, my learning is going really well because the error is going really, really low. But in practice, the error is going low specifically for that data, but it's actually going up for all the rest of the data in the world. So how do you avoid that? You make sure that you have to make sure that your training stops when you're roughly there. If you stop too early, your model is not optimal. You can still learn and make it better. If you stop too late, the test, the error on the test set, and therefore on all the next observations you will make later on will be larger and larger. So you have to find this sweet point here where the learning is optimal. There are different ways of doing that, but the most popular one is what is called early stopping. So you keep an eye on it's not really test set here, it's validation set. You keep an eye on the validation set. And when you see that the error starts increasing again, you stop and you do 1 or 2 steps back. And this is done on the validation set because determining when you stop the learning is a hyperparameter, and that needs to be optimized on a separate set. And then you have still the test set to compute the final measure of performance of your model. So early stopping, and I said that. Okay. Now, another thing to be careful with in practice is unbalanced data sets. This is very common. This happens very often when some classes are very common and some are really rare. So if you're looking at finding rare events and you decide to address that as a classification problem, you have to be really careful. Of course, you could address this problem as an outlier detection, but if you decide to go for a classification angle, be careful that you will have classes that are really rare, classes that are really common, and this would bias the learning because your network, say if you're using deep learning, your neural network or any machine learning method will learn that to optimize this cost here, well, the best strategy to achieve good optimization, good minimization is to focus on the very common class, because the rare class will contribute very little to this minimization problem. So you have to deal with that aspect as well. Otherwise, the rare events will not be considered because they won't penalize the minimization at all, unless you artificially increase their implication in the error computation. So that's something that can be done. So you can, in some methods, you can adjust the weights of different classes to the final, to the empirical risk to ensure they are not being ignored. You could also work on the data itself. You could resample your data to try and even the classes, balance them, or you could try generate some synthetic samples of the rare classes. Or, as I said earlier, try a different perspective, such as outlier detection. Now, specifically in deep learning, because that requires a lot of data, the data augmentation is a very popular solution to increase the size of the data set and the size of the rarer classes. You can think of any data augmentation. There's no limitation. It's just about producing a data sample that is meaningful and that is different from the others. So you could, in this example, you can look at rotations, cropping, translation. Of course, if you translate too much and the object gets out of the image, that's useless. So you have to be careful with the amount of transformation you apply. And you also have to be careful that the data you produce is plausible. In a transformation like this, is unlikely to happen in real life. And so there's no point in training your method to analyze these images. That's not going to help with generalization. You still want your data to be representative of what you expect to get when you use your method later. So be careful with augmentation. You need to be producing some things that are really plausible. Doesn't mean you have to follow strictly some physical rules. Sometimes it's good to give just a bit more variety to let the network learn from, but at least stay within something roughly plausible. This amount of tilt is not very common, but still you can really recognize what's going on. So that's still useful for learning. Right. Last word about training. Once you have trained, you want to measure performance of your okay. So when you're training, after you have trained, you want to measure the performance of your methods. There are different metrics you can use. They are not all equivalent. Of course, they depend on the task. And for the here in an example for the binary classification task, which is by far the most common one, you see that there are quite different measures. Some are more informative than others. For example, especially in case where you have rare classes. So for example, the accuracy, which is found quite often in the literature, is only meaningful when you have balanced classes. If you have rare classes, that's not going to be very illustrative. It's going to be quite biased. So it's not a good, it's not an informative metrics in that case. If you want to stay on the safe side for binary classification, the precision and recall are the standard measures. They are complementary. They always come by 2 by 2. They give you an idea of how many classified items are relevant and how many relevant items have been found. So that's why they are complementary, and they can be combined into what is called the F-score. And that's the really standard metric for binary classification. And then people like to also compute what is called the ROC curve. So when you train a method, sometimes you have a threshold. You have to choose a threshold for your classification. For when the mapping is a label, remember, label can be, say, 1, 1. The method will not give output -1 or 1. It will output a number between these two, and you have to set a threshold. And say below the threshold is -1, above the threshold is equivalent to 1. And depending on where you put your threshold, you're going to have to find more elements or miss more. So you have to make this, this produces when you adjust the threshold, that produces this kind of curves. And so this is a good description of a method which tells you how easily you can find a good working threshold. If a curve goes here, you have a really nice method. If the curve is here, this is practically random classification. So computing the area under this curve gives you a measure of how good your method is, regardless of which threshold you choose. Because the choice of thresholds can be dependent on your aim. If you're aiming to find all the events regardless of how many false positives you have, or if you want to find some events but don't have too many false positives, you're going to choose different thresholds. So this an area under the curve here gives you a good idea of how your method works, regardless of which choice you will make based on the for your threshold. Okay. So now all these methods, learning methods, you can find them in very standard libraries such as scikit-learn or supervised and unsupervised learning. And then PyTorch has become now the most popular framework for deep learning. And you have some high-level wrappers such as Torchlightning as well. So these are the first places to go when you're looking at using these methods. Now, before we focus a bit more on neural networks and deep learning, do you have any question? Do you need a 2-minute break?
I don't, but any questions? Yes.
You said that increasing the size of the annotated samples will converge to the correct solutions, and then you give some methods to improve the learning, but all those methods are at constant size of
Yes.
of data sets. So why? So it's unclear to me why some methods give better results than others.
So the
constant number of data.
So the k-fold cross validation in particular is method to make the most of your data. So you for the given data set, you ensure that you are testing on every single sample once, which means that you are training on all the others at every time. So that's an optimal scheme to really make the most of your data set instead of, because of course you could train on everything, but then you don't have any idea, any estimator of your real risk, because you don't keep data aside to estimate your real risk. So you need to take some data aside to estimate the real risk. That's how you get an estimator of the real risk. And the optimal way of doing that is to train several times to estimate the real risk on all the data samples at least once, and then train on the rest of the data. So you train on as much data as possible, and you estimate your empirical risk on all the data. So it's a way of getting the best possible estimator of the real risk. Of course, if your data set is not representative of your task and too small, that will not solve that problem. That will just give you the best possible estimator of the risk. Maybe that estimator will be bad. Maybe the result will be bad, but at least that's the best you can have. And if that's the case, then you know you need to increase the size of your data set and maybe the diversity of your data set.
Hi, thank you. Could you talk a bit more about how to measure both the real and empirical risk? I'm not sure I followed.
So the real risk, let me go back to the slide that will be easier. Yeah. The real risk, if you wanted to measure it, you will need absolutely all the data that's possible, and all the association of measurements and labels that could possibly happen. That's an infinite number of data, so you cannot. That's why we have to use the empirical risk, which is an estimator of the real one. And so this empirical risk, you can only compute it on this n samples, which is the size of your data set. And that's why there's a link to the first question. That's why you want to get the best possible estimator of the empirical risk by making the most of your n data sample. Because there's just no way you can get all the possible data in the world. Cool. Oh,
Yes.
sorry.
That is kind of my question.
Sorry, I thought you were talking about the empirical and total risk. L is the loss function. So it's how do you compare the mapping produced by your learning method and the label? That's you to decide how you want to compare them, because that's how you decide where you want to put the emphasis on. What do you want to focus on? And also it depends a lot on the type of your data. If you are doing a classification with a scalar label, as we had for the example, you have some very simple ways of comparing. You can do Euclidean distance, you can do mapping, you do your threshold, and then you decide if you're on the right class and have a cost of 0 or 1. You can decide how you do that. There's lots of different ways. Of course, you don't have to design a new loss function yourself every time. You can pick from a large library of available functions. But it's good to have an understanding of what they do, because they don't focus on the same things.
Thank you.
Sorry, it's a bit of a continuation to Lindsay's question. So is the loss function then it can be considered a hyperparameter, or is it?
Yes.
Okay.
It can be, it's usually not, because, well, it's usually not optimized as an hyperparameter, because usually people first think of, how do I want to solve the problem? What do I want to put emphasis on? And I pick the loss function based on that, and they keep it. Although sometimes they find that actually there was a better way of seeing the thing, and maybe I should change loss function. And I have an illustration later when I talk about deep learning, loss function for deep learning, of an example where changing loss function actually really changed the results. So in that case, yes, that's the hyperparameter to optimize.
Yeah, thank you. I had a question about the slide on the oversampling where you showed the green and red curve.
This one?
Yes.
Oh, this one?
Yeah, well, this one or this one. Yes. This function is having one minimum. Are there situations where you have a first minimum and then an increase and then second minimum as you increase the training iterations? Are you almost always in a situation you?
It's rare. What is common is that the curve is noisy. And when the curve is really too noisy and you cannot see a minimum, you need to play a bit with the hyperparameter. The convert is of the optimization. Okay, maybe the convergence is struggling because I don't know, some hyperparameters need to be adjusted, like the learning rate, decay rate, and things like that. Maybe you're overshooting and then coming back too much, and etc. And so the gradient descent is struggling. So you can have this case happen. You can also change the optimizer, and that's another hyperparameter. So there are lots of different variations of gradient descent, for example, and there's a lot of research on optimizing this optimizer and the parameters of the optimizer as well.
I just want to ask a question from the previous slide that you showed. No, the previous slide when people were about the empirical risk. Yeah. So I was you said in practice the PXY, the function is not known. I just want I'm not sure what this.
Oh, okay. Yeah, I didn't detail completely that. So if we look at the full total risk, so what we're looking at is the cost for making an error, and this is weighted by how likely we are to find in real life this particular observation and this particular label.
Okay.
And
But I
so
thought your label is already predetermined.
no, this is not the this is the total risk. So here you're considering all the possible observations and labels that may happen.
Okay.
So an infinite number of combination of observations and labels. And so you're weighting here the error by how likely this observation and label may happen. If your mapping here makes a mistake on something that's really unlikely to be observed in real, then there's not much impact on the total risk. But if you're making a mistake on something that's really common, then you want that to be very impactful. In practice, in the empirical risk, you don't have this weighting because we are considering that the data we have is likely data.
Okay.
That's what we have observed is not something unplausible because we have observed it. So it's probably likely, plausible and likely. And so we make the simplification, the assumption that this data is likely. So we simplify this to 1.
Okay.
So that's why it disappears from here.
Yeah. But in the case of if you have like a really rare, as you mentioned, you have really rare samples.
Yes, this is not exactly the same idea of rare. So rare sample means the event is rare, but it may still happen, and it would be associated with its correct label.
Okay. So this is only associated with how easy that you can identify.
Yes, how likely the observation and the label comes together and exist.
Yeah, thanks.
So I have a question in the same slide. I'm not sure to have fully understood. It seems that for the total risks, there is 2 dimensions, like the one of big X and the one of big Y. And on the second one, there's only 1 dimension, which is like the size of, because it's true.
Yes, so here you're considering all the observations and all the labels.
Yeah.
And whichever combination of them can happen. And that's why P here is useful because you have a weight on how likely you are to see the actual observation label and to see them together. Here you're looking at your data set with an observation and a label that come together and they are stuck together. You're not going to consider all the associations of observations and labels in your data set. This tuple of observation label.
Okay, so it's the same big X for the 2 expression, right? Because like
it's not the same. This here is a subset. Here you have all the observations that may possibly happen. That's an infinite number of observations. While here you only have the n observations that you actually collected and used.
Okay, thank you.
If there's more question, maybe we should discuss them at lunch, at the lunch break, because otherwise we won't have time to look at deep learning. Okay. So now deep learning and neural networks. First of all, why have neural networks become so popular? I said at the very beginning of this lecture that they are a family of machine learning methods. But what makes them so special? This is because, well, in good part, because if you consider the generic data processing pipeline that we saw at the very beginning, where you have some preparation of the data with some steps, very often some steps for reduction or feature extraction, where you try present the data in a way that's more intelligible for the next step of learning. Well, these two steps, they are done automatically by the neural network in deep learning. So these steps don't need to be done manually anymore, and you don't have to be imaginative anymore about how do I present the data in a nicer way, which make more sense. This is being optimized automatically by the neural network. And in computer vision in particular, because the data can be a bit complex to represent in an abstract way, this has been a game changer. And that's why deep learning became so popular, especially in computer vision, because these steps of representing an image into an abstract way where information is easier to find is not always, is often actually quite challenging. And so it's really nice to be able to rely on the optimization process to also optimize this transformation of the data. And so therefore, the neural network is going to learn a transformation for the data, which is maybe not optimum in general sense, but actually works well with the rest of the learning that is being done in this neural network. So when before we had to give image descriptors to a machine learning method, now we just give full image, a raw image, with a minimum preparation. So just making sure the statistics are right, the pixel value range is okay, etc. And then we leave the network, a neural network, figure out how to describe this image in a way that's meaningful so that it can extract the information we are interested in. Of course, that works with other data as well, but it started really being popular with images because this image descriptor engineering was a bit tedious and challenging when it was done manually. This is an illustration of the kind of feature extraction that a neural network would do. In a neural network, so this is a very, very simple neural network, but they all follow this basic principle. You have first layers of neurons, which will learn some low-level descriptors of the image. In this example, then the neurons converged automatically to things which somebody who does image processing would recognize as edge descriptors. Edges so these fine edges with various orientations are also fine color patches. So this is a very low-level way of describing the image. So finding edges with that and that orientation, these patches, etc. And then when we move to the next layers of neural network, the features that are being extracted from these come to something a bit more elaborate with some simple shapes that start emerging, like these circles here, which are probably useful to find wheels of the cars and things like that. And then as you go deeper, higher in the neural network, you get higher and higher level feature. So you see that your neural network learns to describe your data with various stages, going from low-level features to higher and higher level. And this is the automatic data description. which the computer vision people have been really interested in. So how do these neural networks work in practice? This is going to be very similar to what we saw before. So we are learning a mapping function from an entry X to a mapping Y, just like any other machine learning method. And so we're doing the same thing of minimizing the empirical risk to try get the best possible mapping. The only difference is that here the mapping is implemented in practice by this set of neurons, which are organized into layers. And the parameters of your mapping function are the parameters of the neurons. The parameters being some weights between the neurons. So you see, in this way, neural networks are just normal machine learning methods. But and actually, when they were first presented, there was no distinction, not much distinction between neural networks and other machine learning methods. What started, when they started being considered special when they started being bigger, when they got deeper and deeper with more and more neurons and parameters. Because when you increase the size of your neural network, you increase the number of parameters, and so you increase the ability to represent arbitrary mapping functions. When you have more parameters, you can create more complex functions. And so your neural networks is able to learn more complex modeling tasks. And so this is a matter of size here. That's made the deep neural networks so powerful and popular. Of course, there have been also some improvements in the architectures more lately, but initially it was really a matter of size. That was the biggest thing. The size and the size of the training data, which have to come together. Yeah. And also the availability of large computing resources. They all three came together. So how do neural network works in practice? I would recommend you to go and visualize this video. This is a really nice animation. I'm only going to show snippets here, but the video is worth it. It's really nicely animated. It gives a really good overview of how neural network works. So here you have a very basic neural network with just 3 layers of neurons. So they are all the neurons are connected to all the neurons of the next layer and of the previous layer. So that's called a fully connected neural network or a perceptron. That's the most basic neural network you can imagine, and most basic architecture. And this one has been trained to classify, to identify which number is handwritten in this input image. So you take the image, you map each pixel to an entry neuron, and then each neuron being connected to all the neurons in the next layer, etc. At the end, you expect here, because you have written 1, you expect a neuron corresponding to number 1 to be activated. So how that works is each neuron. Can you hear me? So each neuron is performing a very simple operation. It takes all the inputs, so all the values that come from all the neurons of the previous layer, weights each of them by, well, a special weight. There's If there are m inputs, there are m weights. And then sums all these weighted inputs. So it's just a weighted sum of the inputs. And then there's what is called an activation function, which will transform this weighted sum into an output. The activated function brings some non-linearity to the modeling. If you only had this weighted sum, your mapping function H would only be a linear mapping. Here you can have something non-linear thanks to the activation function, so that gives you the ability to model things that are more complex. Now, in practice, what happens in this is nice visual example? Imagine this specific neuron. It has these weights, which are represented in green and red. If you remap that to the 2D format of the image, that shows something like this. So you have negative green, red, and positive green. Well, if you have done image processing, you will recognize that as an edge detector. So in practice, this neuron, specific neuron here, behaves like an edge detector for this location. And so you can imagine other neurons would converge to similar low-level features like this. So they may find edges, diagonal edges in this region, for example, etc. And so the neural network, this is not hard-coded. This is something the neural network converge to during the optimization procedure. And so during optimization, the optimization made it so that this neuron behaves like a detector that finds horizontal edges in this location, which can be useful to, for example, differentiate a 2 or a 7 from a 1, for example. And then when you add, so this is the edge detector. There's usually a bias that is added, which means this neuron only activates when the weighted sum is meaningful. So when it is above this added threshold. And then you add another thing here, which is the nonlinear activation function. And there are a lot of activation functions you can choose from. A popular one nowadays is this one, which means everything negative, you just truncate to 0 and you only keep things that are positive. And so in total, so that can be represented as a matrix format, but that's basically the same thing. This matrix format is really convenient for implementation. It allows to have a fast computing. And so you have your neuron, which behaves like this edge detector which activates meaningfully when the signal is strong enough so that the edge detector output is higher than your threshold and enough to activate your activation function. So this is basic neural networks work. Each neuron here will behave like a filter. And in fact, in some specific architecture, like CNNs, which are for images, they are actually called filter. Now, how do you train your network? That's the question, the example I'm. You have a lot of different possible loss functions for different types of tasks like classification, regression, etc. Autoencoders, we'll see that in a minute. And indeed, when you want to when you are unsatisfied with a result, it may be good to change your loss function. Maybe you didn't pick the one that's the best that gives you the best description of the task you want to solve. And you have an example here of autoencoder. So the task was to reproduce the input image in the output, but after some transformation. And with different loss functions, you get quite different results after a few iterations. These ones give reasonable results, while this one is much more noisy. So it's a good illustration that, and they don't converge at the same speed either. So it's a good illustration that the loss function can have a dramatic impact on your results. And that's quite obvious when you know what's happening under the scene, since the loss function is at the center of your the computation of your empirical risk, which is the very function that is being minimized during the training of your neural network. So that's really the basis of your learning. And that's why the loss function is so essential. Now, I'm just going to give you some an idea of how the training happens in practice. So usually neural network neural networks need typically a large amount of data. How is that? It's because, remember I said 2 slides ago that they can have a lot of parameters, and that's what makes them very powerful, because more parameters mean that the mapping function they can implement can be more complex. And so more complex function, be able to model more complex tasks. But in order to train these many parameters, and this very complex model, you need a lot of data. Otherwise, you end up with this case of overfitting. Because if you have too few examples and a very complex model, which can go all up and down like this, while it's going to match your data so easily, you will overfit in no time. So in order to avoid that, you need enough data to feed your learning. And because you have lots of data, they don't all fit in memory at once. So you have sequential training. So that's why we train on what is called batches. So a batch is just a subset of your training data. So you take a small batch, you train on that. So you train on this small batch, and you use that to adjust the parameters of your mapping function. And then you move to the next batch, you adjust the parameters again, etc. And once you have looped through all the batches, you have done one epoch. And then you do that again. If you use 2 small batches, you're going to train on, I don't know, let's say, take a dramatic example. Let's say you train on 1 image at a time, 1 data sample at a time. You're going to adjust the parameters for that image. And then you get another image which is quite different. You adjust the parameters in a different way. And then another image, you adjust the parameters again. And you're going to go back and forth like this, and your convergence will be really slow. So you want to train on as much data as possible to smooth that out and get an average update to your network, which makes it better on that. But since all the data doesn't fit into memory, you're going to pick the patches that are as big as possible to fit in. And then do several epochs of training. So you train several times on each data until you have some nice convergence. Now, I'm going to go through the most popular types of architectures. The first one is autoencoders. These are the ones for which we had these 3 different loss functions in the previous slide. So the autoencoders have this V shape here, like a butterfly shape, because you have input and output that have the same shape. And in the middle, you're learning some descriptor of your data. And the middle here is a much simpler vector, a much smaller vector in size. So the dimensionality is very much reduced compared to the input size. And you would like this representation to be, well, good enough that you can reproduce your input data just from it. So if you hide this part, you only provide this reduced the representation of your data, this descriptor, it should be able to reconstruct the input data. This is useful in many different applications. The first one is learning, a good representation, which can be used for other things. It can also be useful for denoising. The idea being that you want your network to get some noisy input here, denoised output here, and in the representation here, you want to only keep the useful information and get rid of the noise information. So you want this part here, which learns a descriptor, to learn to focus on the information you're interested in and to get rid of the noise, to not include it in your representation here. And this way, the reconstruction only uses the useful information and you get a denoised output. That's a very, very popular use for autoencoders. Another type of architecture is the recurrent neural network. This is used for processing sequences of data, that time series. The idea you have a set of neurons, and this a memory, which is just a vector. So the memory is updated by this new observation, and then another observation comes in the same neurons, and that updates the memory again, etc., etc. So sequentially, you're going to have the processing of all the sequential observation by the same set of neurons, and every time that updates a memory vector. Remember, and so this memory allows keeping track of what happened previously and adapting how the observation is processed based on that. Another architecture that is popular for is the transformers. This is a bit more recent than the recurrent neural network. So this is a more recent and more complex type of model. It usually has much more parameters. It's also more tricky to train because of that, in part because of that. The idea here is to look at the relationships between, well, within the data. So you have a sequence of data like this sentence, and you're going to look at all the relationships between all the pairs of data samples, well, of samples in your sequence. So for example, here you have this ranking of how relevant, well, how related, sorry, are two samples. And this, which is called the self-attention map, is used to produce a vector representation. So this is a bit more complex than the recurrent neural network, but this is also, excuse me, a bit more powerful. And so a lot of large models for large language models are based on transformers. They have been adapted also to other types of data like images, although the results are a bit unstable. In some tasks, it works well. In some others, it's not as good as the CNNs, which are the last type of neural network I'm going to describe now, which is really specifically designed for images. So earlier, when I showed the description of the neural network, remember with the green and red edge detector, this was for a specific location. Well, in CNNs, the same idea is applied, but these detectors, these filters, instead of being optimized for each detection individually, they are applied to all the possible locations in this way. So you have one filter which is going to be applied in all the positions, and each time that produces an output which creates a new map, a map of activations of that filter. And so this is a bit more efficient because instead of training one filter per location, you just train one filter and you apply it everywhere. And of course, you do that multiple times. So you still train multiple filters, but fewer than for fully connected neural networks. And this is also has the advantage that all spatial locations are treated in the same way, so this is called translational invariance. And this is often a desirable property because you don't want your image to consider, you don't want your network in many cases to consider one part of the image differently than the others. Basically, the physics is the same everywhere. You can introduce other types of invariance as well, actually, such as rotational invariance by using something called pooling, which is basically looking at a small patch and extracting either mean or an average value in this patch and do that in different location. So that can help selecting a same behavior for different filters. And that also helps reducing the size of the data you're working with, because when you do this extraction, you get much smaller maps. And so you work on smaller and smaller objects. So you get a more simplified representation. Okay, so some popular CNN architectures are first the AlexNet, that's the historical classifier. That's what made the neural networks, the deep neural networks, so popular in 2012, I think. Then after that, people started presenting neural networks that can solve multiple tasks. For example, here, so faster CNN first finds salient objects in an image and then classifies them. And then there's a mask RCNN, which is an improvement of that. In addition to the classification, there's also a pixel-wise segmentation of the objects. There's a very fast and lightweight detector called YOLO, which finds roughly, the roughly approximate location of objects. There are some inaccuracies because some simplifications are made to make it fast, but it's quite efficient and very, very popular because it's so lightweight. And many more architecture can be thought of. Something interesting to consider is neural network that share the descriptors, which are called feature maps, to solve multiple tasks. Like here, the detection and the segmentation, here, the detection at different wavelengths, sharing every time the information at the other, considering the information from the other wavelengths as well to get something consistent across wavelengths. These multitask neural networks are interesting because the descriptor that is being optimized for these different tasks. And therefore, it has to be more informative. It has to be more general and more informative. So the training is a bit harder because you're learning to do different models at the same time, but the constraint on the image descriptor that is learned is stronger, and therefore it can give you a more efficient image descriptor. So I'm not saying you should always do multitask learning. I'm saying when you have some complex tasks, some interleaved tasks, it's really interesting to consider doing your own architecture, which allows you to share information between tasks, because that allows learning some more efficient and descriptive descriptor. Now, a little word of warning. How should you interpret the predictions? Especially classifiers. Remember when the classification is a number? I gave an example between -1 and 1 earlier. Sometimes it's just between 0 and 1. And when that's the case, so the output on your network will be normalized between 0 and 1. And people tend to interpret that as a probability. Be careful. This is often not the case. This is not necessarily a probability. It all depends on which loss function you have used. If you have used a loss function called the cross entropy, which is by far the most popular loss function for classifiers, your outputs are normalized between 0 and 1. And when you have several outputs, they sum to 1. So they look like probabilities, but they are not. They're just a score. When you use this loss function, which specifically tries to reproduce a probability distribution. So that's, for example, when you have several people annotating your data set, and they have each given a class. And so you try find a consensus between them. They don't all agree. And so you could say 40% of people think this is class A, 60% think this is class B. When you have these kind of cases and you're trying to reproduce this distribution, then you will use a loss function that's specifically designed to reproduce this distribution, and there the output can be interpreted as a probability, because that's what you're trying to model. You're trying to model a probability. So you see, you have a very different case, and you have some loss function. Which have nothing to do with probabilities. So always be careful when you consider the output. This is not always a probability. This is often just a score. Now, very quickly, I'm not going to go into in depth into the method I'm going to show next. It's just for you to be aware that it exists, so that you can look more at it when you need it. There's often a question of how can we trust the model that is being optimized and the predictions, especially when you have very critical situations like self-driving cars and such. Knowing that we don't have all the data in the world to train with, so our empirical risk is not necessarily the best possible estimator of the real risk. And also knowing that the data can be noisy, uncertain, and in the method I just presented, there's no account of the uncertainty. There are ways to take into account uncertainty, but not in the basic methods. So how do we know how much we can trust these methods? This is particularly This is a particularly important question because there has been already some dramatic failures of these methods. The case of this quite spectacular and dramatic accident was the case that the AI embedded in the self-driving car saw this truck and thought it was an overhead road sign, and so decided to it was just safe to drive underneath. So these kind of accidents, they happen when they happen because the neural network cannot be trained on all the data in the world, and so we are bound to have cases that have not been seen that will be misclassified, misunderstood. There are also cases where methods get very biased simply because they were trained on very biased data. Here, this is a chatbot which got corrupted by people on the internet within 24 hours and had to be disconnected. People just made fun, telling very racist, all the bad thing you can think of, very nice bad things to the chatbot, and the chatbot was learning from the people. And so within 24 hours, it became the most racist, hater possible chatbot, and so had to be disconnected. And here, this app was trained to make people look nicer in picture, but it was only trained on white people. And so it learned to try and whiten Black people to make them look nicer. So that's the case where you have very biased data giving very biased model, and there's plenty of other cases. At some point, I think that was in the US, there have been an attempt to try and make an AI produce some judgments for criminal courts, thinking that would be less biased than human judgments, except that it was made on previous cases which were biased. So of course, it learned to reproduce the bias and give the stronger judgments for Black people. And then there are other cases where models are where it is possible to optimize a noise that you give to a model, a very faint amount of noise. You can see the weight here. So the data doesn't look different to a human eye, but it was optimized so well that the network gets completely confused and produces a very high confidence, with a very high confidence, a very bad label. So this apparently looks like an airliner, while this looks like a pig. This is because this is not a random noise. This was optimized. But it is always possible to optimize a noise to make a network says whatever you want. And you can retrain your network on these examples, and it will get okay on these examples, but it will still have holes, and you will still be able to find another noise to make it say another thing. These are adversarial examples, and it has been shown it always exists. So what you can do is look a bit more into what's going on. And there's a lot of research being done nowadays on what is called explainable AI. One family of methods within explainable AI is to try and visualize what happens within the network and what triggers specific activations of the output neuron. So for example, what triggers the network saying this is 3, and what makes the network says this is a 9. So here you can say that these pixels contribute the most towards a 3 and against a 9. And these sets of methods, they can let you see what the network considers. In this example, you can see network considers mostly the faces of the cats or of the animals, while here it considers also a bit of the background and the general shape of the body. And so it's quite interesting to look at what the network actually looks at, what focuses its attention on when making a decision. Here are a few other examples of the same. So there are lots of different methods, and have a look at the literature. You see this is a always evolving literature because it's a very active research field right now. That also works for other types of networks, like here, a recurrent network, where here we're looking at the activation of one specific neuron, which seems to be focusing its attention on internet addresses, for example. So you can find that for other data types. You can also look at the internal model of a network. Here, this is two works that looked at what are the stereotypical images that a network considers being, well, the different classes it learned from. So this is a more basic, this is a more elaborate method using a GAN. So these are the stereotypical images that the network considers being a mouse, a lipstick, etc. So these are not real images. These have been made by the network, and this is what maximally activates for example, the library class for that network. So these are probably the next foreseeable big developments in AI, the explainable neural networks and all these methods to visualize networks. This is not the only way explainable networks are being investigated. There are other research going on, looking not only at what's going on in the network, but also how to remap the mapping version of network using different methods, which are simpler and more portable. Research in the around that. Another trend that is becoming really big these days is the physics-inspired neural networks. There's one method called PIN. You may have heard about it, where the loss function is a physics equation. So that the output of the network is really constrained by this equation, so that it has to really follow well, it has to produce a physically valid function, valid output, sorry. Physical constraints into the reasoning and the output of a neural network. So this is also an ongoing research topic. And this is related to hybrid models, which combine data and knowledge-driven modeling. So there's more and more methods where analytical models and data-driven models are being combined to try and get the best of both worlds. And this is probably the next, well, at the moment, this is the most popular direction to embed neural networks into physics applications while still getting some guarantees. Well, guarantee is a big word, but almost guarantees of validity of. Okay. So, Sid, do you have any question if there's time?
Do we have time for a few questions? A few minutes for questions?
So I have a question. So how do you decide how many layers are included in the neural network and how many neurons each layer? Is it depend on the dimension of the data set or the number of parameters?
Well, first, just like the choice of loss function, this is a hyperparameter to optimize. Now there are some basic principles that can help you make a good first guess. The first one, as you said, is the complexity of the size of the data set and the complexity of the data set and the task. If you consider your data and you think they all look pretty much the same, there's only small variations, maybe your modeling task is not as complex. And when you have a data set with very varied data, where then you would need more complex models to capture them, to represent them. So the complexity of the task is definitely a key aspect, and the size of the data set as well. Often when you start with a new project, it's a good thing to look at what has been done already in similar tasks and similar data, because some optimization of the architecture has been done a little bit already, and so you can also use that as a first guess and look around these numbers.
Thank you.
So I'm a little confused with the activation function. Is it same as the mapping function?
No. Let me go back to that slide. The mapping function, is the function we saw up here. The mapping function is this function H, which is the mapping that the network is trying to learn from the input to the label. The activation function is within the network. It's for each neuron, there is an activation function which is going to bring a non-linearity to its output. And so each neuron within this network applies this activation function to its output before going to the next layer. And so the mapping function is the overall function that this whole network is implementing. You have to choose it. I gave 3 examples here, which are quite classical, but there's many more and more recent ones as well. Usually, it's a good idea to take a recent one or a popular recent one, because it seems to get good results in many different cases. And often it works in your problem as well. But then if you want to optimize it, you can test with a few different ones. But it's not, I wouldn't say it's as important as choosing a good loss function, for example. The loss function is really, very essential. If you take a recent activation function and a popular one, there's a good chance it gives nice results.
Just a last question, maybe.
There may be differences in the speed of convergence or the optimization.
So when you talk, I was wondering if you have like limited data sets, for example, then would it be better if you have a simpler network so you have less parameters to train and it's easier for them to converge?
So small network, I didn't get
when you have limited data.
Limited data.
Yeah.
Well, again, it depends also on the complexity of the task you want to model. If your task is really complex and your small data set doesn't cover all the possibilities, you won't be able to learn the full thing.
Okay.
So you have first to make sure your data set is representative. so that you have all the possibilities shown in the data set. And then you choose your architecture also based on that. If you see that you need a lot of data to cover all the cases, that means your modeling task is probably quite complex and you need a bigger network. If you don't need so many data to cover it all, then probably your task is not so complex and a smaller network would do.
So when you talk about batch training, does it mean like you train different, like a batch of neurons?
No, you train all the neurons always.
Okay,
If
but
you
like-
truncate a network and remove some neurons, like removing some filters, you would remove part of the descriptor, etc. You just break it. So the batch is batch of images. If you're looking at images, or a batch of data. Where is it? Yeah. So this is the data. So you adjust all the parameters of your network on a small subset of your data. All you can fit in your memory, basically. And then you take the next subset of data, you update all the parameters again, etc., until you've seen all the data. And that's one epoch of training, and then you redo until you have converged. When you're doing multitasking, yes. But you have to be careful with that, because you have to make sure that the overall thing stays coherent. Like if you are training one thing separately, this thing separately from that thing, but this uses that, if you change that after training this one will get confused because the output will have changed. So the output of that and input of that. So to ensure coherence, but yes, it's possible.
Thank you very much, Adeline. If there are extra questions, maybe you can ask during the hands-on. And I think it's time now to go eating.